Section 14.2, dependence of reaction rate on reactant concentration. We saw in section 14.1 that the rate of reaction between bromine and formic acid is proportional to the concentration of bromine, and that the proportionality constant K is the rate constant. We will now explore how the rate constant, and the reactant concentrations are related. The rate law. The equation relating the rate of reaction to the concentration of molecular bromine, rate equals K times the concentration of Br2, is an example of a rate law. The rate law is an equation that relates the rate of reaction to the concentrations of reactants. For the general reaction, A plus B goes to C plus D, where the lowercase letters are the coefficients and the uppercase are the reactants and products, the rate law is equal to rate equals K times the concentration of the first reactant A raised to an X times the concentration of the second reactant B raised to a Y. This is equation 14.2. Let me scroll in here a little bit. That equation is called the rate law, and we're going to use that in calculations. Where K is the rate constant and the exponents X and Y are numbers that must be determined experimentally. When we know the values of K, X, and Y, we can use equation 14.2 to calculate the rate of reaction given the concentrations of A and B. Student note, it is important to emphasize that the exponents in a rate law must be determined from experimental data, and that in general, they are not equal to the coefficients of the chemical equation. In other words, if lowercase a is a 2, that doesn't mean that x is a 2. Or if lowercase b is a 1, that doesn't mean that y is a 1. It could be, it's possible, but we have to determine x and y experimentally, not from the balanced equation. Okay? In the case of the reaction of molecular bromine and formic acid, the rate law is rate equals K times the concentration of Br2 to the X times the concentration of HCOOH to the Y, where X equals 1 and Y equals 0. So that's been determined experimentally. They're telling you that X is equal to 1 and Y is equal to 0. That's not something you can figure out unless you've looked at a bunch of data and figured it out. But they have done that, and they've determined that X is equal to 1 and Y is equal to 0. So notice that Y can be 0. Doesn't have to be 1, doesn't have to be 2. It could be 0. The values of the exponents in the rate law indicate the order of the reaction. So the terminology we use is order. That's actually a mathematical term. So for example, if you have an equation y equals x squared, the order of x is 2. That's called second order. And so we're using the same terminology here. The order of the reaction with respect to each reactant. So each reactant has an order. In the reaction of bromine with formic acid, for example, the exponent for the bromine concentration, x equals 1, means that the reaction is first order with respect to bromine. Okay, so if as x is equal to 1, we call that first order. The exponent of 0 for the formic acid concentration indicates that the reaction is 0th order with respect to formic acid. The sum of x and y is called the overall reaction order. Add them together, x and y, and you get the overall reaction order. Thus, the reaction of bromine with formic acid is first order in bromine, 0th order in formic acid, and first order overall, right? First order overall because 1 plus 0 equals 1. Experimental determination of the rate law. To see how a rate law is determined from experimental data, consider the following reaction between fluorine and chlorine dioxide. So we're now going to look at a different reaction, okay? We're going to leave behind the reaction that we were just looking at. F2 gas plus 2 ClO2 gas, so that's fluorine and chlorine dioxide, form 2 FClO2 gas. That's fluorochlorine dioxide. 2 of them. Rate laws are commonly determined using a table of starting reactant concentrations and initial rates. The initial rate is the instantaneous rate at the beginning of the reaction. By varying the starting concentrations of reactants and observing the changes that result in the initial rate, we can determine how the rate depends on each reactant concentration. Table 14.2 shows the initial rate data for the reaction of fluorine and chlorine dioxide being carried out 3 different times, 3 different experiments. Each time the combination of reactant concentrations is different, and each time the initial rate is different. So what we're doing here is we're doing multiple experiments to figure out how fast the reaction is at the beginning, at time equals 0. The initial rate would be called the instantaneous initial rate. We're going to vary concentrations of the reactants and see what happens. And the reason we're doing this is because we have this idea that the rate is equal to K times the concentration of each reactant to an exponent, X or Y. So by figuring out how the concentrations affect the initial rate, the initial concentrations affect the initial rate, that will tell us what those exponents are. And once we get the exponents, we can find the value of K, the rate constant. So we're going to look through a real nitty-gritty example here. This whole section is very simple. It's just, can you do a very specific type of problem? You've got to be able to do this type of problem. So let's take a look. To determine the values of the exponents x and y in the rate law, rate equals K times F2 to the x times ClO2 to the y, we must compare 2 experiments in which one reactant concentration changes and the other remains constant. For example, we first compare the data from experiments in 1 and 3. Now you might choose different combinations, but follow along, see what their logic is here, okay? So they've yellowed in experiments 1 and 3 to show us that that's what we're going to compare. So if you look at experiment 1, F2 has an initial concentration. I'm going to try to zoom in a little bit here. Experiment 1, F2 is 0.1 molar. In experiment 3, it's doubled to 0.2 molar. Okay, it's doubled. But look at ClO2. No change. We're keeping the concentration of ClO2 the same. So you're picking 2 reactions, 2 experiments, where one changes concentration and the other doesn't. Now, for those 2 experiments, 1 and 3, look what happens to the initial rate. The initial rate went from 1.2 times 10 to the minus 3 molarity per second to 2.4 times 10 to the minus 3 molarity per second. It doubled. In other words, doubling the initial concentration of F2 doubled the initial rate. When the concentration of fluorine doubles with the chlorine dioxide concentration held constant, the rate doubles. So now we're going to go through it mathematically. This is a formal method for solving this problem. The concentration of F2 experiment 3 divided by the concentration of F2 experiment 1 is equal to 0.2 molar divided by 0.1 molar, which is equal to 2. Okay? Now, rate 3 divided by rate 1 is equal to 2.4 times 10 to the minus 3 molarity per second, divided by 1.2 times 10 to the minus 3 molarity per second. That's equal to 2 also. So take a look at what happened. This indicates that the rate is directly proportional to the concentration of fluorine, and the value of x is 1, right? If you double 1 and the rate doubles, if you double the concentration of F2 and the rate doubles, that means that the exponent for x is 1. Student note, recall that when an exponent is 1, it need not be shown. In other words, if the exponent for F2 is 1, we don't need to write it down. Similarly, we can compare experiments 1 and 2. So now take a look at experiments 1 and 2. What happens here? F2 is unchanged, 0.1 molar. ClO2 is quadrupled. It went from 0.01 to 0.04 molar. And look what happened to the rate. The rate quadrupled also. It went from 1.2 times 10 to the minus 3 molarity per second to 4.8 times 10 to the minus 3 molarity per second. So that's quadrupling, okay? So keeping F2 the same but quadrupling ClO2 quadrupled the initial rate. We find that the rate quadruples when the concentration of chlorine dioxide is quadrupled, but the fluorine concentration is held constant. Okay? So in other words, the concentration of ClO2 for experiment 2 divided by the concentration of ClO2 for experiment 1 is equal to 0.04 molar divided by 0.01 molar, which is 4. For those two experiments, rate 2 divided by rate 1 is equal to 4.8 times 10 to the minus 3 molarity per second, divided by 1.2 times 10 to the minus 3 molarity per second. That is also equal to 4. This indicates that the rate is also directly proportional to the concentration of chlorine dioxide. So the value of y is also 1. Thus, we can write the rate law as follows. Rate equals K times the concentration of F2 times the concentration of ClO2. Because the concentrations of F2 and ClO2 are each raised to the first power, we say that the reaction is first order in F2 and first order in ClO2. The reaction is second order overall. 1 plus 1 is 2, right? So if x is 1 and y is 1, 1 plus 1 is 2, second order overall. Knowing the rate law, we can then use the data from any one of the experiments to calculate the rate constant. Using the data for the first experiment in table 14.2, we can write K equals rate over F2 over ClO2. Right? They're both in the denominator, and those are concentrations. You may notice I'm getting a little looser in terms of saying concentration of, but for right now, when we see those brackets, that means concentration of. That ratio is equal to 1.2 times 10 to the minus 3 molarity per second, divided by 0.10 molar, divided by 0.010 molar. And so if you go through the arithmetic on your calculator, and again, when the author, and when I show what the author is doing, and there are calculations to be done, have that calculator handy right next to you and do it yourself. Make sure you get the same number. In general, the examples that they're doing in the textbook, the numbers work out correctly. So if you get a different number, it's most likely you made an error. So take a look at what happens. We get 1.2. And then if you look at the units may look odd to you. M minus 1, S minus 1, right? Doesn't that seem a little odd? That means 1 over molar times 1 over seconds. So in other words, the molarity and the seconds are in the denominator. So they're using this notation where you put minus 1. And how did that work out? Well, the numerator has molarity divided by seconds, but the denominator has molarity and another molarity. So molarity squared. Molarity times molarity is molarity squared. So what happens is one of the molarities in the numerator cancels with 1 in the denominator, and you're left with 1 in the denominator, so that would be written as m minus 1. You also have seconds in the denominator, so that's s minus 1. So the units are there. So the rate constant has some funky units here, right? 1 over molar, 1 over seconds. That happens. Table 14.3 contains initial rate data for the hypothetical reaction. So now, guess what we're doing? We're looking at a different example. This one's more general. This one is not a specific reaction like F2 and ClO2. It's A and B. The author is running out of real examples to use, so we're just going to use a general made-up example. So let me scroll down here a little bit. Table 14.3 is down a little bit from the equation, but the reaction is A plus B goes to C plus D, where the coefficients are lowercase a, lowercase b. Again, the coefficients are not necessarily the exponents, x and y, so we can't just write in a and b as the exponents. The general rate law, rate equals K times the concentration of A to the X times concentration of B to the Y. Comparing experiments 1 and 2, we see that when the concentration of A doubles, with concentration of B unchanged, the rate also doubles. Okay, so table 14.3 has the data. Then below that, they're showing for experiments 1 and 2, the concentration of A doubled and the concentration of B stayed the same, 0.015 molar, and the initial rate doubled. So that's very much like the example we just looked at. If you double the concentration, the initial rate doubles. So that means x is equal to 1, just like it did in the previous example. But now if you look at 1 and 3, they're choosing 1 and 3. Remember, the way you choose them is one of the reactant changes concentration, but the other doesn't. So between 1 and 3, A is not changing, but B is doubling. Take a look, however, what happened to the initial rate. The initial rate for experiments 1 and 3 went from 2.1 times 10 to the minus 4 molarity per second up to 8.4 times 10 to the minus 4 molarity per second. It quadrupled. That's a factor of 4. So what happens then is the rate's not directly proportional to the concentration of B to the first power, but rather it's directly proportional to B to the second power, i.e. y equals 2. Rate is proportional to the concentration of B squared. So the overall rate law is rate equals K times the concentration of A to the first power times the concentration of B to the second power. So overall, this reaction is first order in A, second order in B, and third order overall. Remember, x plus y is the overall order, so 1 plus 2 is 3. Third order. Once again, knowing the rate law, we can use the data from any of the experiments in the table to calculate the rate constant. Using the data from experiment 1, we get K equals rate over the concentration of A to the first power divided by the concentration of B to the second power. Putting in the numbers for that particular experiment 1, again, you can use any of them. It's equal to 2.1 times 10 to the minus 4 molarity per second divided by 0.10 molar divided by 0.015 molar squared. That would be equal to, again, use your calculator to get the same number, 9.3 molarity to the minus 2 seconds to the minus 1. Why are those units working out the way they do? Well, take a look. You've got molarity in the numerator, but you've got molarity, and you've got molarity squared in the denominator. So you have 3 molarities in the denominator. That's molarity cubed. So if you cancel 1 molarity in the numerator from 1 in the denominator, you have 2 in the denominator. So that's molarity to the minus 2. And of course, we still have the seconds to the minus 1. Note that the units of this rate constant are different from those for the rate constant we calculated for the F2ClO2 reaction and the bromine reaction. In fact, the units of a rate constant depend on the overall order of the reaction. Table 14.4 compares the units of the rate constant for reactions that are 0th, 1st, 2nd, and 3rd order overall. Those are essentially the only 4 possibilities that you would see in this course. So table 14.4 says, look, here's our overall reaction order. Here are the units. So you can take a look at those units right there. Now, the following are 3 important things to remember about the rate law. The exponents in the rate law must be determined from the table of experimental data. In other words, those examples we just did. In general, they are not related to the stoichiometric coefficients in the balanced chemical equation. I've said that a couple of times. Comparing changes in the individual reactant concentrations with changes in rate shows how the rate depends on the reactant concentration. Reaction order is generally defined in terms of reactant concentrations rather than product concentrations. Okay, now I'm just going to briefly mention that you will notice that we're only using the reactants for the rate law, not the products. Okay? Sample 14.3 shows how the initial rate data, how to use the initial rate data to determine a rate law. So again, that sample problems will be different videos. So sample problem 14.3, of course, you want to try them, and then you want to do the practice problems, and you want to do the checkpoints. But that pretty much is it for this section. Our next section will be 14.3, the effect of time.